Good morning, everyone. So today we will discuss about seismic stratigraphy. So now, as I already told, that seismic stratigraphy is basically a stratigraphic study based on sequences. Now, the seismic study or seismological study was first done by an English seismologist, Robert Mallet. He tried to identify, or he tried to study the seismic waves coming from the interior of the earth. He started his study by some experimental works in the laboratory in 1840. Basically, the aim of the study is to record and study the natural seismic waves coming from the inside of the earth during some earthquakes or during several um, times, and by studying those natural waves, whether we are able to identify the subsurface layers or subsurface rock types by this method. So basically, seismic stratigraphy developed as a science particularly for studying the subsurface lithologies, particularly the deep arts, because as a human being or as a um, instrument, you can dig certain levels in the crust beyond which we cannot go directly. So for that, for deeper earth condition, we have to depend on the indirect evidences, and seismic studies help us in this way. দেখতে পাচ্ছিস তো? আমাকে একটু হোয়াটসঅ্যাপে রিপ্লাই কর প্লিজ, দেখতে পাচ্ছিস কিনা স্লাইডটা? Okay. So as I told that there are many ways of classifying or studying the surface rock records, such as lithostratigraphy, biostratigraphy, chronostratigraphy, and other sequence stratigraphy. Others are also there. But peoples in the uh, 20th century, or they are interested, they gradually feel interested about the subsurface layer, particularly the oil sector peoples, the petroleum geologists, the coal geologists. They are interested that what was beneath and where the economic valuable things such as petroleum, coal, where they occur. So due to that, they have to depend on some indirect methods to know about the subsurface layers. And from that, seismic stratigraphy came into the scenario and becomes very much popular among the geologists. Now, the concept of seismic stratigraphy is very simple. Here, in the surface, in certain points, uh, and these waves or sound waves, they go beneath the surface. When they hit the surface interval, that is when this medium, this layer is changed and another layer comes in this interval surface. When this wave hits an interval surface, from this interval surface these waves are reflected back again to the surface, and in the surface, in some fixed intervals, there are some receptors. In seismological term, we call them as seismometers, or we call them as geophones. Basically, record the reflected wave. Okay, that wave may be a normal vibratory wave, that wave may be a sound wave. So we create some waves in the source region. They goes below the surface when there is difference in uh, layers observed. That means composition within the layers are changed. Along the interface, the rays are reflected back again to the surface. There are some receptors which we called geophones, and these geophones are collecting the reflected uh, amount of wave. Now, starting from this source to the geophones, the wave have to travel two times the same distance. First is goes to the interface, then again comes to the surface. So if I try to depict or try to find the depth of this interface, basically this depth is related with respect to the time taken by the wave to go from the source to this interface and reflected back to the receptor, and the velocity of the wave. So if the total time taken from the source and the receptor receive is suppose delta t, then delta t is equal to 2h. That means this one is 1h and this one is another h, so 2h divided by v, that is 2 times step and the velocity of the wave within that medium. So this equation is for a single layer or two layer model, when or where there is only a single uh, layer interface. From that interface, the rays are reflected back and they are collected in different geoforms. So depending on the different time interval, obviously this first geophone receives the fast reflected ray, because this amount of uh, h, or this amount of 2h definitely is lower than the this amount. So the ray has to cover lower distance. In the second receptor, the ray has to cover more distance than the first one. So ray recovered here or collected here little later than the first geophone, and it is the last receptor where at last the last signal of reflected ray is recorded. So from the different time recordings of different geophones, we have to calculate a complex equation. Basically, we did not do that. All these geophones are connected with a computer which runs a sophisticated software, and by running that software, the computer basically calibrated the depth of this interface. So this is for a single interface. We are knowing the depth of this interface from the surface. Now, if there is multiple layers, so from the source, when we generate some waves that will reflect from the first interface and goes to the receptor. Similarly, it goes in the second interface, goes to the receptor, goes to the third interface, and then reflected back to the receptor. So in each and every layer interface, that is whenever the ray face some kinds of change in lithology, and due to this change in lithology, the density of this medium or the density of this layer is changed, and due to that the velocity of that particular wave within that layer is also different. So the first layer, if I depict it as L1, which occurs up to h1 depth from the surface, in this layer the ray velocity will be v1, and this layer has a density of d1 or rho1. Now, when this layer changes and a different layer comes, which occurs up to H2 depth, here the density will be D2 or ρ2, and the velocity of ray will be V2. Successively, D3 or ρ3, the density, the velocity will be V3, and the depth is H3. So, you can see each time the characteristics of the layer, that means the composition of the layer by which the density of the layer is dependent, that is changed in each layers, and due to that the incoming ray suffers some kinds of change in lithology, and due to that it reflected back from the layer interface again to the surface and collected by the geophones or seismometers. Okay, so by this method, you can see that if we are able to know the H1 depth, that means the first interface depth, similarly uh, we are able to know the second interface depth, we are able to know the third interface depth, and like on we are we can go far depth from the surface. Now, when the depth of penetration of any incoming ray or any incoming wave is low, we get very high resolution of reflected uh, rays. But when the depth of penetration, that means the incoming waves or incoming rays goes to higher depths, then the resolution comes is very low. Suppose here you can see in this uh, arbitrary picture, when a wave generated from surface and goes only this shallow depth, you can identify all the small folds, all the horizontal layers, all these things. So your resolution of this reflected ray is very good, so that you can identify all those structures very precisely or accurately. But when in this left hand picture you can see that a wave generated and goes far depth within the subsurface and then reflected back. So due to the penetration far within the depth and then reflecting back again to the surface, some amount of energy destroyed. So very less amount of energy is basically reflected back and collected to the geophones. So the depth wise or more depth subsurface image is not very clear, only a very crude scenario can be observed. So for the same wave, it gives better resolution for near surface rocks, but uh, for deeper rocks, the resolution is not very good. So to avoid this problem, scientists or people introduced different devices to resolve this problem. So some kinds of devices are very much useful for shallow depth lithologies, to understand the shallow depth lithologies, to understand the shallow depth layerings, and some kinds of instruments or devices are configured to understand the deeper part of the earth. So those devices are not very good for the shallower depth rock layers. Now, why a certain instrument is not good for all depth within the earth? You can see here, whenever some incident light is falling within the interface of two mediums or two layers, then depending on the angle of incidence, some amount of ray or some amount of wave is reflected back to the surface or reflected back towards the source region, along with some amount of ray is transmitted to the next medium. So a incoming light or incoming wave coming from the top portion of the medium 1 falling on the interface of medium 1 and medium 2, some portion is reflected back again to the top portion of medium 1 and some portion goes to the medium 2, which is known as refracted wave or transmitted wave. So the amount of incident wave is not entirely reflected back to the top portion of the medium 1. So that is why this reflected wave or reflected ray, the amount, the energy condition of this reflected ray is always smaller, far smaller than the amount of incident ray or incident wave. So more and more transmission or more and more refraction will occur, the lesser and lesser amount of reflected ray coming to the Earth's surface. Now, the reflection of the incoming wave or incoming ray is dependent on the velocity and density of the layers. Suppose here are two layers, layer 1 and layer 2, and this is their interface. Now an incident ray fall on the interface of layer 1 and layer 2. Some amount of incident wave is reflected back to the surface and some amount is transmitted to the deeper portion. Now the amount of reflected wave, that is how much wave or how much energy is reflected from this interface between the two layers, that depends on the acoustic impedance of the two layers. Now what is acoustic impedance? It is basically the multiplication of two properties. One is the velocity of the wave within that layer and the density of the layer. So the acoustic impedance of layer 1 is the multiplication of velocity and density, that is V1 and D1, and the acoustic impedance of layer 2 is the multiplication of V2 and D2. Now, how much amount of wave or how much amount of energy is reflected back to the surface? That is the primary concern for a geologist or for a geophysicist. Okay, because that is the main concern, because these reflected waves are the only waves which are collected in the surface geophones, surface receptors, and from that we can interpret the subsurface layerings. So how much amount of reflection will occur from the interface between layer 1 and layer 2, that is basically dependent on the reflection coefficient, and it is determined by some mathematical formula, which is basically the difference between the acoustic impedance of these two layers. Okay, so more and more difference in acoustic impedance of these two layers, more and more reflection of the incoming wave will occur. Now, the greater the amount of reflection will occur, the more amount of energy or more amount of waves is reflected. So, higher amount of resolution of the reflected wave or the subsurface is captured in the geophones. So we get better picture or better resolution on the subsurface layers. Now, at the same time, when the reflection value is very high, that means a major portion of the incoming wave is reflected back. So only a very minute fraction of the incoming wave is transmitted or refracted more towards the deeper part. So due to that, the deeper part energy transmission as is already very low, so the deeper part subsurface layers resolution is poor. So when the reflectivity is high, reflection coefficient is high, more amount of reflection will occur from the interface and more amount of reflected wave is captured in the surface geophones or surface receptors. So we get more and more information about this particular interface, that is the interface between layer 1 and layer 2. But if there is more subsurface layers, as the transmitted wave amount is very less, so from that reflection will occur, the reflected wave amount is again far low than this amount of transmitted waves. So gradually the reflection from layer 3 and layer 4 are lesser and lesser and lesser. So we will get far lesser and lesser values of reflected wave in the receptors from layer 3 and layer 4. Okay, so basically the amount of reflection is high, we get a more and more clear picture of the interface between two layers. When the amount of reflection is poor, then most of the incoming waves or most of the incoming energy that is transmitted deeper within the deeper part of the earth, and when in the deeper part of the uh, reflection coefficient is high, then we get more amount of reflection, so more amount of reflection is captured within the surface geophones and we get good picture or better resolution on the deeper part of the earth. So if acoustic impedance difference uh, is higher in the shallow layers, then we cannot get better picture of the deeper layers in the subsurface. If the acoustic impedance of the shallow part layers is low, then we can get a better picture of the deeper part of the earth layers. Now here you can see the acoustic impedance of different layers. Here is a artificial or a schematic section of different rock layers. The acoustic impedance of different layers. Here for this sand bodies, the acoustic impedance is high. For these shelly layers, acoustic impedance is low. Again, for the limestone, acoustic impedance is high. Sandstone or this is siltstone, acoustic impedance is low. Shale again very low, and limestone again very high. So reflectivity coefficient, here you can see that the acoustic impedance of sand and shale is very high. The difference between acoustic impedance of sandstone and this shale is very high. So you can see the reflectivity coefficient between the interface of these two layers is high. Similarly, the acoustic impedance of shale and limestone is also high. High means the difference. The difference may be in the positive side or maybe in the negative side, whatever it may be. If the difference is high, the acoustic impedance difference is high, then reflectivity coefficient will also be high. But when this difference is low, the difference of acoustic impedance between two layers is low, you can see the reflectivity coefficient is also low. So more amount of acoustic impedance between two layers, the higher amount of reflection coefficient. The lesser difference in acoustic impedance between two layers, the lesser amount of reflection coefficient. Now, here is a methodology by which you can see, or here is a diagram. Here you can see reflection from different layers. So here it is the source from where the waves are generated. At the surface, at fixed interval, the receptors or geophones are located, and this is not the actual positions. Basically, in practical purpose in the field, these geophones are located in fixed interval, but in this diagram it is arbitrary diagram. So here you cannot see the fixed distance from different geophones, but in actually these geophones, successive geophones, are located at fixed interval from the previous one. So uh, from the surface, some waves are generated and they are reflected from different interfaces. So when they hit the first interface between the sand layer and shell layer, some amount is reflected back and received in the first receptor, some amount of wave is transmitted far below in the interface between layer 2 and layer 3, basically the shale and limestone. Again, some amount of wave is reflected back to the surface, some amount of goes deeper part. So like this way, we the reflection of any incoming wave occur from different interfaces of layers, and these reflections are recorded in the surface receptors or geophones which are occurred in the surface. Now, the wave generated in the surface, if we try to complicate the phenomenon a little bit, the wave generated surface is first goes to the interface and received in the first receptor. Similarly, the waves are going in all directions. So the waves generated here also falls in this interface and reflected back to the second geophone. Similarly, the fast from the fast interface, the reflected waves are also received in the other geophones also. Okay, and there are some internal reflection also. Suppose the waves fall in this interface, reflected back. Now there is also an property change between the layers. So this is the rock layers, this is the sand layers, and this is the surface condition, and above this sand layers there is air. So from sand and air there is also characteristic change. So between the interface of this sand body and the upper atmosphere, in this interface some amount of reflection can again occur. So that is called reflection within the layers, and this reflection goes again to the first interface, then again reflected and received in the other geophones. So you can see basically, and similarly this can happen in these layers also, these layers also. So you can see that a single geophone will receive multiple number of reflected waves at different time intervals. Now, for a person being, it is very difficult to separate it out that which reflected wave received by the geophones is coming from which layer intervals. Okay, so here in the second geophone, whether it receives this black lined reflected wave or it is received this dotted line reflected wave at some time interval t2. Okay, so for a human being, this calculation is very difficult. So for that, all these geophones are connected to a highly sophisticated computer, and there some software are already installed that will do all the calculations and give us some images or give them some information about the subsurface layerings. Now the very simple informations about the subsurface rocks, what we get is the layer spacing, that is the distance between two successive layers. Here you can see that the distance between layers are moderate. Here you can see the distance between two successive layers are uh, more or less same, but here in the lower part the distance is little high, but in this portion the distance between two layers is low. Here you can see the more distant occurring of layerings. That means that here the layers are very thick compared to these two, as this black colored lines are basically uh, indicate the intervals between two layers, the interface between two layers. Okay, and the first thing is the frequency of spacing is uh, informed by the computer of the subsurface rocks, and second, the continuity of the layerings. Here you can see the layers are discontinuous, patchy. Here you can see a little bit continuous, little bit more continuous than this one. Here you can see the layers are more continuous, prolonged uh, distance, and here you can see that the layers are continuous and more closely spaced. So the first hand information we get from the computers about the subsurface conditions, that is the continuity of the subsurface layers and the spacing of the subsurface layers. That means spacing means the thickness of the subsurface layers. Now we can also interpret the different inclination of the subsurface layers, and on the basis of that different terminologies are developed. These are already discussed in your sequence stratigraphy class, that is on lap, down lap, top lap, and off lap. Okay. So basically, um, on lap and off lap are the horizontal layers, and down lap and top lap are uh, implied or used for the inclined layers, the inclined layers relationships with the upper and lower horizontal layers. Okay. Now this one is a seismic profile of the subsurface condition. Here we can see all the layers. You can see some layers are very closely spaced. Here you can see some layers are more distantly spaced. You can see the distance between these two layers is far than the distance between these two layers. And you can also see that the layers are become carved due to some intrusion. Here some intrusion, forceful injection of some intrusive body occurred, and due to that these lower layers are carved and there are some discontinuity surfaces generated. Those are the faults by which the layers become discontinuous, but in the upper part again the layers becomes horizontal. Okay, so more or less all the subsurface lithologies, their continuities, their thickness, their gross or broad structures within the rock layers, that can be observed from the seismic profile. And as you know that different, this seismic profile is drawn on the basis of certain physical characters of the layers, that is the velocity and density. So as the density of each and every rock layers is different, so each and every rock layer will show different types of reflected phenomena. Similarly, if there is any uh, fluid, that may be water, that may be petroleum, so as they are also chemically different, so those two fluids, oil and water, will also show different kinds of seismic reflection. So by that, we can identify the subsurface occurrence of any important mineral or subsurface occurrence of any important natural fuel. So that's all. That's a brief introduction about seismic stratigraphy. Uh, Hope you will understand. Thank you.